first of all, I mean, we've talked about this a couple of times, but you will get 4 FRQs on your AP exam. 2 with a calculator, 2 with not a calculator. One of the ones without the calculator is guaranteed to be the sinusoidal function, which is what we'll get to soon, okay? And then the other one will usually have something to do with like logs, which we're about to get into, and trig identities and that kind of stuff, which we'll also get to. And then in the 2 calculator questions, there's usually one where you have to build a model like we did with the exponential stuff, where you got given like the population and you had to build a model. You have to use the model to predict it. It just doesn't have to be exponential. It could be exponential, it could be long, it could be sine, it could be a whole bunch of different things, okay? And then there's one like this, where it gives you composite functions, inverse functions, somehow built in, okay? So this you would have a calculator on, but obviously there's parts of it that you don't use the calculator. The instructions say the figure shows the graph of the function f. So we know that that's one of the functions and it's labeled f on its domain of negative 3.5 to positive 3.5. The points negative 3, 1, 0, 1, and 3, 1 are on the graph, which it's stated, but also you can conclude that those are those 3 points. And then the function g is given by g of x equals, and it gives you an exponential function. So we've got a g of x, and we've got the f of x, that is the graph. A1, so this question is worth 6 points. Each single, like I is 1 point, I is 1 point, each of them are 1 point, okay? So you'd be going, like being scored out of 6. Same for the other 4. So as a total on your FRQs, you're scored out of a total of 24 points, okay? So function h is defined by g of f of x. Find the value of h of 3 as a decimal approximation or indicate if it's not defined. So we are doing g of f of 3. F of 3 comes from my graph. So if I find f of 3 from the graph, what's its value? 1. So then I'm finding g of 1, which means I'm going to take 1 and I'm going to plug it into the equation. 2.916 times 0.7 to the first, which means it's really just 2.916. Oh, let me get my calculator. 2.916 times 0.7. And then this answer would have gotten given 2 different answers, one if you rounded and one if you truncated. Both of those would have been marked as correct, okay? I will always round, so like, if, you know, just to be consistent with multiple choice and stuff like that, I'll round. But you can also truncate, which means like just drop it off. So this one, in both cases, were the same. Actually, it would have been h of 3 equals 2.041. Did we get it right? Yes, give yourself a point. It's a well-earned point. The errors on this, so they will tell you partial credit is awarded for. If you round incorrectly, like if you only rounded in 2 decimal places, they will give you partial credit. Okay, but don't do that because that's a silly way to lose points. You need every point you can get. Yeah.
Is the reason we use f of 3 because we need h of 3?
You need h of 3, and h is g of f.
Okay, so the starting value has to be the same as the end as h of 3. Like we need because
H goes in here, right? So g of f of x is h. And you're finding h of 3. So 3 goes on the input on the innermost one, which is the f of x. Yep. All right, number 2, or AII says find all the values of x for which f of x equals 1. F of x is our graph. If we look at our graph, what are the values of x in which f of x equals 1? That's one of them, right? It says find all the values of x for which f of x equals 0. So what are my values of x for which f of x equals 1? Negative 3, 0, and 3. Okay, you could literally just list them. So and you really just needed 2.041. You didn't have to write h of 3 equals that. Is 2. I is negative 3, 0, 3 in any order. And you can write x equals negative 3, 0, 3. Or you could just write those. How many of you got that one right? Give yourself a point. So that's the second point, okay? BI says find all the values of x as decimal approximations for which g of x equals 2 or indicate that there's no such value. So now g is my exponential function, right? So I pulled it up on Desmos, but you could have done this on your handheld calculator. You could either set this equal to 2 and have to solve using logs, which we haven't reviewed yet, Eventually we'll get there. Or, oh, did I just lose it? Or you could type in your equation. So y equals 2.916 times 0.7 to the x. And then I make my other y 2. And I want to see where they cross. It's only once, and it has 1.057. So BI is 1.057. Raise your hand if you got it right. Okay, give yourself another point. I says determine the end behavior of G as X increases without bound. So it's talking about increases without bound. Is that the right hand or the left hand behavior of my function? Right hand behavior. And it says use limit notation. So I'm going to say the limit as X goes to positive infinity, because that would be right hand behavior. And my equation is named G of X. So I'm going to say G of X equals what's happening on the right hand side of your graph. Where's it going? To 0, because there's a horizontal asymptote there. So full credit for that entire thing. Partial credit was awarded if you gave like the limit notation, like if the answer was right, but maybe the limit notation wasn't right, okay? If you just gave G of X equals 0, they gave partial credit for it. And then C says determine if F has an inverse function. So we're going to come back up here. Does F have an inverse function? No. How do you know that? So CI is no, and that gets you a point. How do you know it doesn't have an inverse function? Okay, horizontal line test is how we test for it, right? If it crosses through here, it fails. But the explanation on it, and this is where it gets trickier because you have to include a whole bunch of stuff. It says give a reason for your answer based on the definition of a function and the graph of y equals f of x. So I'm going to say it is not a function, or it does not have an inverse, sorry. Does not have an inverse because each output is not mapped from a unique input. Saying it fails horizontal test will not get you. Saying it's not one-to-one will not get you. And not even that is enough. We have to say why. So for example, what makes this fail that test is, for example, both f of negative 3 and f of 0, or f of negative 3 and f of 3, or f of 0 and f of any two combinations of those equal 1. That's for CII. Yeah.
Why wouldn't it be each input is not mapped?
Because it's the output that can't repeat for invertible.
But it is a unique input for each y value.
No, the y value is repeated on negative 3, 0, and 1.
Yeah, the y value, but the input is the x value. It says it's not mapped from a unique input, but it does have each y value has a unique input. It's just not.
No, there's a y value that has a repeated input.
Same x value?
Correct. Right? Y1 is your output. It's not mapped from a unique input. There are multiple inputs that gave you the same output.
But doesn't unique mean not the same? Because they're different numbers.
They're not. Right. They would have to be so if for a y can't repeat with a different x.
Oh, okay.
That would make it fail the horizontal line test. That's
Yeah.
basically what you're saying.
But the wording, it's not mapped from a unique input. The y value 1 has 3 different
Inputs.
But those inputs are different numbers. It's negative 3, 0, and 3, which are separate numbers, different. So how is it not a unique input?
The No, it's though it has to go both ways. Each output has to be tied to a unique input. Each input has to be tied to a unique output. It's both ways. Because one passes the function test, one passes the horizontal line test. So one, it has to be a function in order for it to even work. And then it also has to be that the y value cannot repeat with a different input.
So if some point each input is not mapped for a unique output,
It wouldn't be a function. So it's got to be both in order for it to be an invertible function. Each input has to be mapped to a unique output. Each output has to be mapped to a unique input. It has to be both. But you have to say why. This is, or for example, why, using this specific example. So in order to get that point, you had to do all of that. Yeah.
So like.
All right, we're moving on to logs. So the logs, log expressions, log functions, log graphs are the next couple of units or sections. Sorry. We are going to pause after this one, and then you'll take your quiz. But we'll keep going and eventually get through more log stuff. We'll do properties of logs. We'll do graphs of logs. We'll do regressions of logs. Okay, and that will be on your test. But for the quiz, it's going to stop with this stuff. So a log, and hopefully you remember a little bit of this from Algebra 2, but a log is basically just another way to write an exponential statement. It is its inverse, okay? So a couple of things about like how we would even say this. This is log base A of x is how we would read that statement out loud, okay? And we can have it as just an expression where it literally just says like log base A of x. In which, if we are going to simplify this, we're always asking ourselves, is there a power I can raise the base to get to the thing that's next to it? That's how we simplify a log, okay? The very basic foundation of logs is how we go back and forth between log and exponential. And the way we do that is that the base on the log comes over and picks up the other side, and it drops off, leaving what it's next to originally by itself. So if it looked like this, the A comes over and picks up the Y and drops off, and it would be equal to the X. So whether you're going from log to exponential or exponential back to log, the two that are paired together at the beginning never stay together. So here my A and my X are together. They part ways when I put it into exponential. And vice versa, if my statement is exponential and I want to write it in log, the base on the exponential function becomes the base on the log. So this would be log. The A becomes the base on the log, and the A and the Y part. So the Y goes to the other side, and the X joins the log. So the two that are together at the beginning never stay together in the next statement, okay? Obviously, in function notation, that Y changes to f of x. So these are also functions. All right, so we're going from log form to exponential form, okay? And then you could also go from exponential to log. In order to do this, this statement itself has to be true. So this is my log statement, log base 2 of 8 equals 3. And that is only true because 2 to the third equals 8, okay? So we got to know how to go from exponential to log and log to exponential. These are inverses of each other, okay? So a common log is log base 10. If you see the word log, you have to know that that means log base 10, okay? On your calculator, spot your little log button. It's next to your 7. It says log. That is log base 10. I will show you that there's a place on your graphing utilities that you can change your base. But if you are just using log itself, it is log base 10. Okay, which means log of 10 is equal to 1 because log is log base 10 of 10. So remember, we're asking ourselves, what can we raise this power to get to this? Well, 10 to the first is 10. So if the numbers are next to each other are the same, my answer is 1. Because that would be raised to the first power to get to the other log. All right, rewrite the log equation as an exponential equation or vice versa the other way around. So on A, the 4 comes across the equal sign and picks up the -1, drops off, and leaves the 1/4. Left and right could be switched, like the order doesn't matter. But that's how we rewrite it. For B, what becomes the base on the log? 25. So log base 25, this is now gone. I bring the 5 to meet it, and I bump the 1/2 to the other side. So again, the pairing always splits up. So log base 25 of 5 is 1/2. So look at, if I didn't have the 1/2, could you have figured this out? Think the base has to be raised to what power to get you to the bigger number that's next to it, right? So 25 to go to 5 means it's a square root, right? And a square root is a fractional exponent. That would be 1/2. All right, let's see if we could do these. So short, and what you want to get to is, I don't even have to rewrite this in exponential form. I just know it. Ask yourself, what can I raise the base to get to the number next to it? Should you get tripped up, you can always say, okay, this equals x. So 3 to what power gives me 3. And if the bases are the same, you can set the exponents equal to each other. Or you can usually figure it out from there. But hopefully we get to the point that we could just do these like people who don't like to do a lot of work, like logs, because it's a lot of mental math. What is log base 3 of 3? 1. What is log base 3 of 81? 4. What is log base 3 of -9? Trick question. It's impossible. It's impossible. A -2, a -2 moves it, right? A negative on an exponent would move it. It would be 1/9. But there is no power I could raise a positive number to make it negative. So if what's next to the log is negative or 0, it's no solution. It can never happen. All right, D, log base 36 of 1/6. Good. Negative because it moved from a whole number to the denominator. 1/2 because it went from 36 to 6, which is a square root. Log 1,000, 3. Just got to count the zeros on that 10 because it's 10 to what power? And log base 3 of 1? 0, because anything to the 0 power is 1. Yep.
For E, is it log 1 to 1?
No, the base is 10 on log.
Oh.
Yep. All right, now example, what are we on? 3. Says evaluate without using a calculator, then with. So the way we do this, well, there's really 3 ways to do this. If I'm going to estimate it, okay, I'm saying 3 to what power gives me 17, right? If I'm estimating, then I want to figure out what power of 3 comes before 17, what power of 3 comes after 17. So what's 3 to the what comes before? 3 squared would come before because that's 9. And 3 to the third is 27, so that's after it. So 17 is somewhere in between here, right? If it's about halfway, we say a 0.5. If it's a little bit closer to 27, we would say a 0.8, a 0.7, whatever it is that's closer. And if it was closer to 9, I would go that way. So it's about 8 away from 9, and it's 10 away from 27. So maybe it's like a 2.4, maybe, okay? Again, it's approximation. All right, now grab your calculators. There's 2 ways to do this. One, if your calculator does not have a change of base, then we use what's called the change of base formula, which is the log of the number in the bigger position, not value-wise bigger, but the number that's next to the log goes in the top over the log of the base. Base goes to the bottom. This will give me the same answer as log base 3 of 17, and so will ln of 17 over ln of 3, because ln is just a log. ln is log base e, if you remember that, okay? So I can test both those out. Log of 17, either close your parentheses or hit enter, then divided by log of 3, I get 2.5789. Or ln of 17 divided by ln of 3, same answer, 2.5789. Than what we estimated? Yeah, but we guessed. It's not an exact science because you're raising to a power. So the middle is not really middle, if that makes sense, right? Yeah. Okay, so now, yeah. Huh?
On the right is same as this.
This is another way of writing this. Yep, this is called the ratio of common logs, and this is the ratio of
exact point.
this would be more accurate than this, yeah?
When you use a calculator.
But your calculator also has a change of base. So if you click on math on your TIs, if you hit math, and you scroll down past the screen, I think it's 0. No, it's A. It says log base. If you hit that, you can physically change the base to 3 and then hit 17. You get the same answer. But you can physically change your base. Everybody did that? Found it? Math, arrow down to A. And it says log base.
So you just do math
Where?
and then it goes to.
Where?
Yeah. Did you hit math?
Oh, A.
And then go down to A. You see it? So, quiz, no calculator. You'd be approximating, okay? Not quiz with, by the time you get to your test, there's going to be times in which we have to use the base.
Anything from 2.2 to 2.8?
No, because you.
I mean, a little bit more centralized, but yeah.
So like you just say, 'cause, like, if it's closer to the 9, we have to be below.
Yeah.
5.
Yeah.
If it's closer to 27.
Well, but it's 2.57. That's right.
But
That would be
like,
close. It is closer to the 9.
If we're estimating without the calculators.
Yeah.
It has to be like either below.
Yeah, I would say probably a 2.3 to a 2.8. I would have given you it because it's an estimate. You got to at least know you're in between those two numbers. Okay. All right. Now let's talk about how these are used. So there's a lot of like actual real world application on logs. We use it in chemistry for pH scales. You use it in like, they use it on the Richter scale. The Richter scale is actually a log scale. So this one says the log scale is used to display numerical data over a wide range of values to make it easier to visualize / work with. For example, and there's a question on your AP homework that brings up the Richter scale, okay? And so I wanted to give you a little bit of knowledge based on it before you go in blind. The Richter scale uses base 10 to measure an earthquake, so magnitude 2.0 is actually 10 times more intense than 1.0. But it's not that I just say, oh, it would be like 10 difference. Each decimal place away is your exponent on your 10. So this is one whole number, so the difference is 10 to the first. If it was two whole numbers, it'd be 10 to the second, okay? But if it's a decimal difference, so 1.0 to 1.2, that is 0.2 difference, but it's not that it's 10 times 0.2, it's 10 to the 0.2, okay? So it's gonna ask you like, what's the difference between this scale and this scale? You find the difference, and that is the exponent on the 10, because each tenth is like another 10, if that makes sense. So the difference in the magnitude is the exponent on the 10. That'll help you answer one of the questions on your AP classroom. Unless you guys are very knowledgeable on Richter scales, which I was not, so I had to learn. Yeah. Okay, then you'll get to something like this. The sales of a new car in cars per month is modeled by the expression 350 log 25t plus 60, where t represents the time since the sales the car began. How many cars are sold per month for time t equals 40? So what are you going to do? Plug it in. This is 350, if it would write. 350 log 25 times 40 plus 60. Then I'm going to multiply 25 times 40. 350 log times what? 1,000 plus 60. And then before I can do anything on the outside, I got to find this, right? What's the base on that log? 10. So what is log of 1,000? 3. So this is 350 times 3 plus 60. Oops. So 1,110 cars were sold. No, sorry. How long is it? No, the sales. $1,110. No, it is how many cars. I was right the first time. Sorry. How many cars? Okay, since time being 40. So notice we didn't need a calculator on that. There are going to be models in which it wouldn't simplify and you'd need a calculator and you could use your log, change base, whatever. And then there's going to be times in which you can do it without and you would be expected to do it without the calculator.
Okay, so we do like the Richter scale column, right?
The Richter scale?
Yeah, if it was like, if my like exponent was 0.3, it would be 0.3 times 1 times.
It'd be 10 to the 0.03.
Can you just ending, right?
Yeah.
It'll
The difference
always
is
work.
the
It's just
exponent.
put.
You just came up with that number all popped out of your head, huh?
If we do the math thing, then.
Any questions on today's notes? Okay.